Today we can continue molecular orbital theory. When we study molecular orbital theory, we have to study some terms, that is bond order and magnetic properties. Bond order is defined as half of the difference between number of electrons in the bonding molecular orbital and number of electrons in the anti-bonding molecular orbital. We can write the equation bond order is equal to half into Nb minus Na. Nb means number of electrons in bonding molecular orbital, BMO. Na means number of electrons in anti-bonding molecular orbital. Then you will get bond order, a value. For example, in hydrogen, you know there are only 2 electrons in hydrogen molecule. One from one hydrogen atom and the other from the other hydrogen atom. When these two hydrogen combines to form a single molecule, it has only 2 electrons. And that 2 electrons will enter into a bonding molecular orbit. So what is the bond order? Half into number of electrons in bonding molecular orbital 2 minus Na. There is no electron in anti-bonding molecular orbital, that is 0. Half into 2 minus 0 equal to 1. 1 will be the bond order for hydrogen. Paramagnetic and diamagnetic properties. Here we are considering only paramagnetic and diamagnetic properties of molecules. Using molecular orbital theory, it is possible to find out the magnetic property of the molecule, whether it is diamagnetic or paramagnetic. In the molecule, if there is an unpaired electron, it has paramagnetic property. And what is paramagnetic property? The substance will be slightly attracted in the magnetic field, or it will act as a magnet in presence of an external magnetic field. That is paramagnetic property. So in paramagnetic substance, there will be an unpaired electron in the molecular orbit. And the molecule will be attracted in the magnetic field. Now what is diamagnetic? If there is no unpaired electron, or if all the electrons are paired, then the substance has diamagnetic property. What is diamagnetic property? It will be weakly repelled in magnetic field. It will be repelled in magnetic field. That is diamagnetic property. An example is H2O. If you bring a strong magnet near to water, H2O, you can see the repulsion of the water. That is diamagnetic property. If all the electrons in the molecular orbitals are paired, the molecule will be weakly repelled in the magnetic field. Such molecules are diamagnetic. Now, what is the relationship between stability and bond order? Molecules with the positive value of bond order exist. Molecules with the positive value of bond order exist. Molecules with the bond order 0 or negative do not exist. If the bond order is 0 or negative, we can say that molecule will not exist. The molecule will exist only if it has a positive value of bond order. So molecules with a positive value of bond order exist. Molecules with the bond order 0 or negative do not exist. And the stability of the molecules increases with increase in the value of bond order. Stability of molecule increases with increase in the value of bond order. So you have two molecules. One has bond order 3 and the other one has bond order 2.5. Which is more stable? The molecule with the bond order 3 is more stable. Now we can see the drawing of molecular orbital diagrams, MO diagrams. The first one is hydrogen. As I already mentioned, hydrogen atom has 1 electron and hydrogen molecule has 2 electrons. When you draw the molecular orbital diagram, the left side you have to show the increasing direction of energy. So here it is clear, energy is increasing in this direction. Here it is represented as hydrogen, that is to represent the atomic orbitals of first hydrogen atom. And here again you can see a hydrogen atom, that is to represent the atomic orbital of this orbitals of this hydrogen atom. Now in the middle, H2 hydrogen molecule. So in the middle you have to show the molecular orbitals of hydrogen molecule. Okay, now it is the molecular orbital diagram of hydrogen. When you draw molecular orbital diagram, you have to show the atomic orbitals and the molecular orbitals. In the first hydrogen atom, there is 1 electron in the 1s orbital, 1s1, that is represented here. In the second hydrogen atom also, there is 1 electron in the 1s orbital, that is represented here, 1s1. When these two atomic orbitals undergoing linear combination, additive overlapping results in the formation of bonding molecular orbital with lower energy, that is sigma 1s. And subtractive overlapping results in the formation of anti-bonding molecular orbital sigma star 1s with a higher energy. So electron filling will take place in the increasing order of energy of molecular orbitals. So first electrons will enter into sigma 1s. Here there are only 2 electrons, so this orbital will be filled and there is no electron in the anti-bonding molecular orbital. So bond order half into Nb minus Na, that is equal to half into 2 minus 0 equal to 1. Since the electrons are paired, there is no unpaired electron. Electrons are paired, it has diamagnetic property. Now the next one, He2. Helium has 2 atomic orbitals, 2 electrons. The atomic orbital has 2 electrons. So when 2 helium atoms combine, you will get helium molecule. Helium molecule, it has 4 electrons. Here, as we already explained, the energy increases in this order. And here you can see atomic orbital. This one again atomic orbital, and it is He2 molecule. And these two are molecular orbitals. Here in this helium, there are 2 electrons. In this helium, there are 2 electrons, total 4 electrons. And by the linear combination of atomic orbitals 1s and 1s, we will get sigma 1s and sigma star 1s. First 2 electrons will enter into sigma 1s and the remaining 2 electrons will enter here sigma star 2s. And when you calculate the bond order, you can see 2 minus 2, 0 divided by 2 equal to 0. Bond order is 0, so it does not exist. Since the bond order is 0, He2 molecule cannot exist. So this molecule is not possible. Why? Bond order is 0. And what is the magnetic property? No question of magnetic property, why it is not existing, then why there is magnetic property? No need to ask the magnetic property of this molecule, the reason it is not existing. Now C2, no, there is no such molecule, C2. But there is C2 radicals, C2 radical is there. Okay, whether it is possible, whether C2 can exist or not, we can draw the molecular orbital diagram of C2 to consider the electronic configuration of carbon 1s2, 2s2, 2p2. Out of this 2s2, 2p2 are the valence electrons or valence orbitals, 2s and 2p. So here we can consider the linear combination of 2s and 2p orbitals. Here you can see 2s orbitals are undergoing linear combination to form sigma 2s and sigma star 2s. And here 2p orbitals, 3 2p orbitals here, 3 2p orbitals here. So total 6 atomic orbitals are undergoing linear combination. As a result, 6 molecular orbitals will form. Already we mentioned the order of increasing order of energy of molecular orbitals for molecules up to nitrogen N2. And in the case of p orbital, the lower energy is for pi 2px and pi 2py. Both of them are having same energy. Pi 2px and pi 2py, lower in energy. Then comes sigma 2p search, then pi star 2px, pi star 2py, then sigma star 2p search. So here now in the outermost orbital or valence shell of carbon, how many electrons are present? 4 electrons. And from the 2 carbon atoms, total 8 electrons. We will get 8 electrons. The first 2 electrons will enter here, sigma 2s. The remaining 2 electrons will enter, the next 2 electrons will enter in sigma stars 2s. So 4 plus 2 will enter here pi 2px, pi 2py, plus 2. Again enter pi 2px, pi 2py. All the 8 electrons are present here now. But you have to understand inner orbital. 1s orbital also carrying a pair of electrons. They also can undergo linear combination and there will be sigma 1s and sigma star 1s. Don't forget that. For convenience, we are representing only the outermost orbitals here. Okay, what is the bond order? How many electrons in the bonding molecular orbital? 2, 4, 6. 6 electrons in the bonding molecular orbital. Minus how many in the antibonding? Here you can see 2 in the antibonding molecular orbital. 6 minus 2, 4 divided by 2, 2. Bond order half into Nb minus Na is equal to 2. Half into 6 minus 2 equal to 2. And this molecule is diamagnetic. What is the reason? You observe the molecular orbitals. In molecular orbitals, only paired electrons are present. If there are only paired electrons in the molecular orbital, that substance will be diamagnetic. So it is diamagnetic. And what is the electronic configuration? You can see sigma. Already there is sigma 1s and sigma star 1s. So sigma 1s2, sigma star 1s2, sigma 2s2. You can look here. Sigma star 2s2, pi 2px2, pi 2py2. That is the electronic configuration of C2. Now we can see the case of N2. N2, again, the distribution is same, increasing order of molecular orbitals are in the same order. Sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2p z, pi star 2px, pi star 2py, sigma star 2p z. And the valence shell of nitrogen, how many electrons? 2p, 2s2, 2p3, 5 electrons. From the 2 nitrogen atoms total, 10 electrons. 2. Out of this 10 electron, 2 enters here, remaining 2 here, next to 2 here. So 4, 6 is remaining. 2 plus 2 plus 2, 6. All the electrons are entered into the molecular orbitals, and here it is over. This is the molecular orbital diagram of nitrogen. Now what is bond order? Calculate number of electron pairs in bonding molecular orbital. 2, 4, 6, 8. 8 electrons in the bonding molecular orbital. How many in the antibonding? 2. Half into 8 minus 2 is equal to 3. Bond order is 3. What about the magnetic property? All the electrons are paired in the molecular orbital. All the electrons are paired. Therefore, it is diamagnetic in nature. In the molecular orbitals, all the electrons are paired. That means in the molecule, there is no unpaired electron. So it is diamagnetic. What is the electron configuration? Don't forget sigma 1s and sigma star 1s. Start from there. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. Now, in the case of the next molecule, that is oxygen, there is a slight change in the increasing order of energy of molecular orbitals. Here, after sigma star 2s, pi 2px, pi 2py, then comes sigma 2pz. But in oxygen, after sigma star 2s, sigma 2pz is the molecular orbital. And pi 2px and pi 2py are higher in energy than sigma 2pz. Okay, that we can see here. This is a case of oxygen. The atomic orbitals of oxygen 2s, 2p, valence shell is considered. Next oxygen 2s and 2p. What is the electronic configuration? Atomic atom of oxygen 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. And here you can see 2s2, 2p4. 2s2, 2p. There are also 2s2, 2p4. Only the valence shell is considered. And the molecular orbitals, as in all other cases, here also sigma 1s and sigma star 1s are present. That is not in the valence shell, so we are not considering it to represent the molecular orbital diagram here. Now, the molecular orbital sigma 2s, 2s and 2s are atomic orbitals undergoing linear combination to form sigma 2s as sigma star 2s antibonding molecular orbital. Sigma star 2s, in the case of p orbitals, when they combine, here you can see the change. First, sigma 2pz. In all other cases, the cases that we discussed earlier, here pi 2px and pi 2py, but here sigma 2pz. Sigma 2pz, then pi 2px and pi 2py of same energy, pi star 2px and pi star 2py of same energy. Finally, sigma star 2pz. A total how many electrons? Here 2 plus 4, 6 electrons in one oxygen, valence shell of one oxygen, and when we consider valence shell of the other oxygen, total 12 electrons. First 2 ended here, now remaining 10. Next 2 ended here, remaining 8. Next 2 ended here, remaining 6. Next 2 here, remaining 4. Again 2 more here, remaining 2. Now only 2 electrons are remaining. These 2 orbitals are of same energy. So by following Hund's rule of maximum multiplicity, each orbital will get 1 electron. So 1 electron here, 1 electron here, 2 unpaired electrons. So it is the molecular orbital diagram of oxygen. And here you can see 2 unpaired electrons are present in the molecular orbital. So oxygen is paramagnetic in nature. Oxygen is paramagnetic in nature. What is the reason? Because of the presence of 2 unpaired electrons in the molecular orbital of oxygen. Pi star 2px and pi star 2py contain 1 electron each. Therefore, it is paramagnetic. And what is the bond order? The green orbitals represent bonding molecular orbitals. 2, 4, 6, 8. 8 minus 2, 3, 4. 4. Bond order half into 8 minus 4 is equal to 2. Now what is the electronic configuration? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2, pi 2p y2, pi star 2p x1, pi star 2p y1. Here you can see it. Now the next case is of fluorine. Fluorine, how many? What is the electronic configuration of fluorine atom? 1s2, 2s2, 2p5. 1s2, 2s2, 2p5. And it also will follow the increasing order of energy as in the case of oxygen. That means sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2pz. So we can draw the molecular orbital diagram. It is the molecular orbital diagram. 5 plus 2, 7. You can see 5 plus 2, 7. 7 plus 7, 14 electrons are present. 2 here, plus 2 here, 4. Plus 2, 6. Plus 2, 8. Plus 2, 10. Plus 2, 12. Plus 2, 14. All the 14 electrons are entered here. Now what is the bond order? Count the number of electrons in the bonding molecular orbital. 2, 4, 6, 8. How many electrons in the antibonding molecular orbital? 2, 4, 6. 8 minus 6 equal to 2 divided by 2, 1. So bond order is 1. Half into 8 minus 6 equal to 1. What about the magnetic property? Consider the molecular orbitals. Is there any unpaired electron? No, there is no unpaired electron. All the electrons are paired. So it is diamagnetic. F2 is diamagnetic. No unpaired electrons in it. No unpaired electrons in it. So F2 is diamagnetic. In the slide it is given as a mistake. It is given as a mistake. It is given as paramagnetic. It is not paramagnetic. It is diamagnetic. It is diamagnetic due to not absence of unpaired electrons. It is diamagnetic due to absence of unpaired electrons. Okay. F2 molecular orbitals, bond order is 1, and F2 is diamagnetic due to absence of unpaired electrons. All the electrons are paired. Now the configuration, sigma 1s2, sigma star 1s2, that is there already. And the valence shell, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2, pi 2p y2, pi star 2p x2, pi star 2p y2. That is the electronic configuration. Okay, now two questions for you. Which of the following is more stable and why? O2, O2 plus and O2 minus. What you have to do? Already you know the electronic configuration of oxygen. What is the electronic configuration of oxygen? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2, pi 2p y2, pi star 2p x1, pi star 2p y1. And you know what is the bond order? That is 2. 8 minus 6. Sorry, 8 minus 4 divided by 2. Bond order is 2. In O2 plus, instead of 6 plus 6, 12 electron, there will be only 6 plus 5, 11 electron in O2 plus. O2 plus means there is loss of 1 electron. So from 12, if you subtract 1, you will get 11 electrons. There are only 11 electrons. So in the antibonding molecular orbital pi star 2py, there will be no electron. That electron is lost. There is no electron in pi star 2p. So number of electrons in antibonding molecular orbital reduces from 4 to 3. So what is the bond order? 8 minus 3 by 2 equal to 2.5. O2 plus bond order 2.5, O2 bond order 2. Now the next case, O2 minus. O2 minus means one more electron. Now 12 electron in oxygen plus 1 electron, 13 electrons. So 1 electron will be more in antibody molecular orbital, pi star 2px2. So bond order half into 8 minus, instead of 4, 5. 8 minus 5. 3 by 2 equal to 1.5. So which is more stable? O2 plus is more stable because it has bond order 2.5. O2 has only 2 and O2 minus has only 1.5. The next one you have to solve it. Now hydrogen bonding. The attractive force between hydrogen atom of one molecule and a more electronegative atom of another molecule is known as hydrogen bond. When we mention more electronegative, you have to consider only fluorine, oxygen, and nitrogen. Here it is clearly explained in HF. Because of the polarity of HF bond, fluorine has negative charge and hydrogen has positive charge. So hydrogen atom of one molecule will be attracted by fluorine atom of another molecule, and these dotted lines represent the hydrogen bond. It is HF covalent bond, and this dotted line hydrogen bond between hydrogen and fluorine. There are two types of hydrogen bonds: intermolecular hydrogen bond and intramolecular hydrogen bond. What is meant by intermolecular hydrogen bond? It is formed between two different molecules of the same or different compounds. Here you can see it is formed between two different molecules of same compound, isn't it? Two different molecules of same compound, HF. Hydrogen bond is formed. Another example, H2. Then NH3, H2, NH3, HF, all these can form hydrogen bond. Because of hydrogen bond, H2O exists in liquid state at ordinary temperature. H2O is liquid at ordinary temperature. Why? Because of hydrogen bond. But H2S is a gas. There is no hydrogen bond. So the H2S is a gas. HF is a liquid because of hydrogen bond. But HCl is a gas. There is no hydrogen bond in HCl. Now, what is intramolecular hydrogen bond? It is formed when hydrogen atom is present in between the two highly electronegative atoms. For example, fluorine, oxygen, or nitrogen. Here you can see in orthonitrophenol, NO2 group, NO2 nitro, OH group phenol. So OH group is attached to benzene ring, NO2 group also attached to benzene ring. If OH group is attached to benzene ring, that is phenol. And since in the ortho position or second position nitro group is present, we will call it as orthonitrophenol. In orthonitrophenol, this hydrogen is bonded to this oxygen atom, more electronegative, so it will get a partial negative to positive charge for this hydrogen. Here nitrogen and oxygen is more electronegative than nitrogen, so it will get a partial negative charge. So here develops an attraction between hydrogen and oxygen. So it is an intramolecular hydrogen bond. Because of the presence of intramolecular hydrogen bond, orthonitrophenol has lower melting point. Orthonitrophenol has lower boiling point, not melting point, lower boiling point than that of paranitrophenol. What is paranitrophenol? This NO2 group will be present here. So there is no chance for intramolecular hydrogen bond, but there is intermolecular hydrogen bond. So paranitrophenol has higher boiling point than orthonitrophenol because of the presence of intermolecular hydrogen bond. But orthonitrophenol has intramolecular hydrogen bond, so its boiling point is lesser than paranitrophenol. Like this, the chapter is over. You can stop it here, and you have to write down the assignment and submit it.